All right. I know you guys love a good video. I also know you love a good day off for me. So today's like a win-win. Okie dokie, recursive formulas and summation. Both things sound equally fun. When the pattern used to describe a sequence is related to the previous term, not the term number. Explicit was related to the term number directly, but today you're going to be looking at the previous term and seeing how are they changing term to term, which we saw in yesterday's problems also. The formula used to describe it is called recursive. And the notation for the previous term, as we talked about yesterday, is a subscript n minus 1. Because if I'm cruising along here, first term, second term, third term, oopsies, and so on, at some point I get to the nth term. The one after that would be one higher, and the one before it would be one lower as a subscript. So this previous term is what we're talking about. So yesterday we had like 1, 3, 5, 7 or something, let's say. And it's harder to tie that back to the term number and think, how am I getting that? But what a lot of you saw right away is it's going up by 2. So you are adding 2 to the previous term. So that kind of horizontal link sometimes is easier to see. So I wrote that up there, but what's meant to be here is that A1, A2, and then you're going to have A sub n minus 1, and then your term that you're trying to find. Okay, so this is kind of just as easy, but this one's going to have 2 equal signs. So 2 equal signs, maybe even more. So let's put greater than or equal to. We should use that when we can. And if you took notes yesterday, then you saw that I wrote 1 equal sign because it has to tell you where to start. So everyone's favorite thing to do wrong is to not write that number down, but they're telling you the first term is 2. And then this is telling you to get any other term, take the previous term and add 5. So I'm just going to add 5, and so on. So my pattern is based on the previous term, oopsies, not necessarily based on the term number. So it's easier to generate the terms in a lot of ways, but it's not easier to do this because in order to find this, I would need all 99 terms because I need the 99th term to add 5 to it to get that value. So definitely recursive is not as user-friendly in terms of sort of the long-term, farther out term values, whereas yesterday with explicit, we could just type in, or excuse me, plug in the 100, plug in the 16. So just to kind of conceptualize like which one's easier for what, when can I use them if you're given options. So generating the terms is pretty easy because they give them to you. For example, this one that starts as a -3 because they're telling you the first term. To get every other term, you're going to take 2, and then this notation doesn't mean anything except the previous term. So I'm going to take 2 times the previous term and then add 1. And then here, I'll take 2 times the previous term and add 1, and so on. So 2 times the previous term plus 1. So those are easy to generate, but again, hard to get something that's farther out. And then here, the reason I said it might have more than 1 equal sign is something like this. This is telling you your first term is 1. It's telling you straight up that your second term is 3. And it's telling you that because it utilizes both of those previous terms. So this is the term before what you're looking for. And then this one is one before that. So you're looking further back. So what they're trying to say is here, to fill the third term, I'm going to add the one right before it plus the one before that. So I'd be adding the 1 and the 3 to generate this value. Now to fill this space, I'm going to add the 2 terms before that to get that value, and so on down the line. So when you go to write a recursive formula, these will be easier again to recognize a lot of times. And so you have to say where to start. So you have to kind of say where to start and then what to do. So this one you're saying, hey, start at 1. And then you can write a comma or write it in this as a second row. Then you're saying to get any term, what should you do to the previous term? So like the example I used above, which happens to be this exact example, these are going up by 2. So you would show that you're using the previous term. Make sure you keep that -1 or -1 down in the basement because that's a subscript. And then you're taking that entire previous term and adding 2. So this is telling you where to start. This is telling you what to do to move on to the next term. Take a look at this next one and kind of think about how can you get those. And if you look at it long enough, it's kind of one of these. So again, with experience, you'll start to kind of get some idea of what are they doing. So here it looks like they're using these two, adding them together to get that one. Then the next two to get the next one. So this is going to be one where you have to say, hey, the first number is 1 and the second number is also 1. And in order to get any of the numbers after that, you're going to take the number before it plus the number before that and add them together. So because it requires 2 numbers to create the next number, you have to tell people what those first 2 numbers are, and then they can build from there. Okay, and this set of numbers is just a famous sequence. It has a ton of applications in science and nature. It's called the Fibonacci sequence, or the Fibonacci numbers. If you Google it, there's a ton of videos, ton of information. I don't know if you would have talked about it in science or not. Leads into the golden ratio and a bunch of other things. You can either find, or you can ignore it altogether. But it's just kind of a thing to know. Like all the cool people know about that, so you should know about that. Okay, so now yesterday we talked about how to do something that looks like this, and it has to do with a -1, but now we're not tying it back to that term number. We're not saying how is it related to term number 1, 2, 3, 4, 5 like we did yesterday. Yesterday we did an explicit formula that would have said, hey, to get any term, take -1 to a power. And then in this case, we talked about needing to make that power n+1 because it starts positive. But that's explicit. And what we need to do today is figure out how are they changing as you go. Tie it back to the original. We have to say where to start. That's part of a recursive. And then now we're going to say, okay, to find the next term, you're going to take the previous term and do what? So in order to use this one you have and get a -1 next, and then get a +1 after that, what are you doing? And some of you kind of tied into this yesterday when I asked for the pattern. So you already saw that you would take -1 and multiply it by that previous term. So you weren't wrong. You were just looking at the recursive format rather than the explicit, because this is going to be our recursive where it builds on the previous. So starting to understand the difference between those two is going to really be important. All right. So apparently I only have posted for you guys the first page of these notes, so that's not really perfectly awesome. Okay, so here, this is going to be where a series, oh, I lied. I don't want to have that yet. Sorry. A summation is used to add the terms because we have not really done that, but now we're going to start to add the terms together. And so you're going to use this, which is a sigma. And we sometimes call that sum or summation notation. Hang on one second. I want to make sure that I have a filled in version of these notes that I can post for you guys, because I don't know why I'm doing this right during our video, but that's kind of how I roll. Want to make sure that I have that for you. Yeah, well, I'm not sure I do. I'll check when I get to school. So anyway, sigma or summation notation is just indicating that you're going to add up the terms. This is the term number. This is going to be where you start, or you can think of it as the first number you plug in. Typically a 0 or a 1, but not always. So look, this is going to be where you stop plugging numbers in. And this is going to be like the explicit formula that you plug into to generate terms. And when you do that, you'll generate an a sub 1 plus an a sub 2 second term plus a third, all the way out until you get to whatever this is. So if that top number is a 5, you're going to be going until you plug in 5 and then stop. And so it turns into adding them all together, and you'll actually just get a number in the end then. Hang on, I'm still looking for this because I'm obsessed with finding it for you now. Which I guess is probably like super duper irritating to you guys. All right. So let's do this. The math of this is very easy. It can be kind of tedious depending on how many numbers they give you or how far you have to go. So what this is asking you to do is to start by plugging in a 1 for I, stop when you get to 5, and then add up all the terms, summation. So I'll do 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4 and plus 3 times 5. So I'm going to end up with 3 plus 6 plus 9 plus 12 plus 15. So I'm not smart enough to do that. And I got 45. So my answer is 45 because it's summation. I'm supposed to find the sum of the terms. When you do that, those are called a series. A series is a sum. The sequence that we've been talking about is simply a list. So if you have a sequence, you're going to have the first term, then the second term, third term, and so on. When you have a sum, you're going to have the first term plus the second term plus the third term, and so on. So just, again, kind of starting to understand the vocabulary and being careful to know that everything, like the words really matter in terms of all of that. All right, let's keep rolling. And again, once you get how to do this, you certainly can just hop to your homework. So here I'm going to start at 3. Be careful. We get in the habit, I know I do, of assuming it starts at 1, but you can't. And then I'm going to stop at 6. So I'll have 1 plus 3 squared, 1 plus 4 squared, plus 1 plus 5 squared, and 1 plus 6 squared. So this will be 10 plus 17 plus 26 plus 37. These are the places that I love to make mistakes, and I know some of you do too, because you go too fast. And so just take your time when you're doing this. And so the sum of 1 plus k squared from 3 to 6 turns out to be 90. All right, so this one is a little confusing, but we are smart, mostly you guys, and so you should be good, except for now I zoomed away from it. So what this is telling me is that I am going to be starting with 1 and going to infinity, which I don't really have that kind of time. So we're going to use our big brains to figure out what would happen. We would have this as our first term, this as our second, this as our third, and so on until forever. So this will turn into 3/10 plus 3/100 plus 3/1000, and so on. So think about it. They believe you can do this, so there has to be a way. Think about decimals. This is 3/10. This is 3/100. This is 3/1000. If I add those together so far, I'll be at 0.333. By the way, that's called a partial sum. So it would be the third partial sum because I did the first 3. So I added up that part of it. Now, if you keep going, it's going to keep going. So this is going to generate 0.3 repeating, which we talked about yesterday. Anytime you have that repeating number, it's going to be that number over 9, which in this case would reduce. So then I can get that sum as I go. Also keep in mind, every step we're taking here, it gets really small, a lot smaller. 3/10 versus 300ths versus 3,000ths, then 10,000ths, 100,000ths, and so on. So that 1/3 is a really good value, even though you can never get to infinity. When you have 3 over infinity, it's basically 0. So you're not adding anything of significance on there. Okie doke. So here, again, try not to freak out about finding the formula. Just look at how you might be able to build it, keeping in mind that just like yesterday, when you have the sigma, you're going to be counting from 1 to 2 to 2, 3, and 4, and so on. So let's take a look. When I look at this problem, I see that these are all 5s. It never changes. So I'm going to throw down a 5 up here because that never changes. I also see that these are all 1s on the bottom left, and they're all plus. So I don't have anything shady like a sign change going on. So I have 5 over 1 plus 1, 1 plus 2, 3, and so on to 15. This is my first, second, third term. So the term number is exactly what I'm seeing down here, which must make this the 15th term. So I would go from, and it doesn't matter what letter, this can be an I, a J, a K, whatever it's going to be. So I equals 1, and then I'm going up to here where I stopped by plugging in a 15, and I would write it like this. Actually, I would write an I there. I was going to write an N. Whatever letter you use at the bottom of the sigma is the letter you plug in here. So you'll notice even up in these examples right above, if they used a K down in the bottom part, then they would use a K here. So you're just plugging in from 1 to 15 into this spot. It's not asking you to find the sum. It's just saying use the notation to write the sum. Okay, so let's do that. Look for patterns. Recognize numbers. 2, 4, 8, 128. Think about what that number pattern looks like. And again, the more experience you have, the better that will be for you. I can see that the top stays 1. Even this first one's 1 over 1. But I also can see that I have alternating signs. And so the first one's positive. So let's think about how we did that yesterday. Okay. So there's nothing you can do except think about it and try to figure it out. Well, these are all powers of 2. This first one is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, and then if you keep going out to 128, that is going to tell you your last term, because that is 2 to the 7th. So let's look though. This is our first term, second, third, fourth, and we don't know what. So look at the relationship. Here I have the first term, 2 to the 0. The second term, 2 to the first. Third term, 2 to the second. So you can see that this is always 1 less than the term number. So let's say that we're going to start and just use n. We're going to start at 1. We have a 1 on the top, but we'll deal with that in a second because we need the signs to alternate. And on the bottom, we have 2 to a power, but the power is 1 less than what we're plugging in. So the power is going to be n minus 1. And if this is a 7, which is 1 less than the term we're on, this must be term 8. So I'm going to stop at 8. Now, I need them to go back and forth. So we learned how to do that yesterday. We make that negative. And if you want to start with a positive, you need to have a power of n plus 1, or you could use n minus 1. As long as you're putting a plus or minus 1, you're moving away from -1 to the first power and giving it a chance to turn positive in that first term. So I'm done. Some of you will see it right away. Some of you will have to hunt around. And sometimes you just have to get better at it as you go. But learn from your experience. Like I'm looking at this next one and I'm noticing this is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, and 2 to the sixth. There's no dots. I can see the beginning, I can see the end. So my summation, since I'm doing term 1, 2, 3, 4, 5, and 6, I know that I'm starting at term 1, I'm stopping at term 6, and I can see that the bottom is 2. And in these problems, can you see that the power it's raised to is actually identical to the term number? So that means this is going to be 2 to the n power. How about the top? The top is definitely harder to figure out. The only way you start to recognize some of those number patterns is to do the math we've been doing on a regular basis. One of the things that's common in sequence and series is factorial. So we talked about that yesterday. I don't expect you to recognize the factorial numbers, but this would be 1 factorial, 2 factorial, 3 factorial, 6, 4 factorial, 5 factorial is 120, and 6 factorial is 720. So the number that we're doing the factorial of to get the top is equal to the term number. And we're calling that n, not k or I in this problem. So I have n factorial on the top and 2 to the nth power on the bottom. And just like yesterday, it's a lot easier with the fractions to say like what's going on with the top, what's going on with the bottom, and come up with 2 separate rules for that. Okay, so we are winding down. There are some kind of properties, I guess. Hang on. Okay, so usually I choke to death, but apparently today I'm going to sneeze. I'm waiting because I think I might be sneezing again. Or I might not. Definitely clearing up, I think. Okay, let's hammer this out. I'm sorry. You guys should get like hazard pay because I'm your teacher. So this is just a constant, meaning a number. It doesn't have a place to plug in I. So the first one is going to be a C, whatever that constant is. So is the second term. So is this third term, and so on until you get to whatever this nth term is. So in this case, whatever your C is just gets multiplied by the number of them that you'll use. What does that mean? Let's say you went from I equals 1 to 4, but you're using 3's. If I go to do that, my first term is a 3, my second term is a 3, my third term is a 3, and my fourth term is a 3. And I'm supposed to stop when I get to the fourth term. So I have 4 3's. So I'm multiplying my constant by the number of them that I used. So that's what that notation means. If you have a constant inside getting multiplied by your formula, you can just take that out. It's just saying, hey, whether you can just pull like a 2 or a 3 or whatever you have out of there and then get the sum of this. So you can either include it every single term or just take it out in front. Because if I generated terms using it, I'd have that constant times A1, that constant times A2, that constant times A3 forever. And so it's kind of like undistributing. You're just saying, I'm going to pull that out in front and then just figure out the terms without it, knowing that in the end, my answer would have the same value because of distributing. So that's just saying you can take a constant out front, and here you can multiply the constant by however many repetitions you have. If you have the sum or difference of 2 different formulas within your sigma, you can either do them all at once or you can separate them. You can figure out what's the sum of just this first rule from I equals 1 to n, and then I can add or subtract, depending on what it said here, to the sum of this. So I would figure out the one number sum of the terms in A, then I would figure out this one number sum of the terms in B, add them or subtract them. So properties are what properties are, right? Like the distributive property is just a thing you can do and your answer comes out the same whether you distribute the number or not. So these are just properties, things you can do, but your answer will come out the same either way. And then the last one, our infinite series, is kind of what we talked about, and we're going to get into this a little bit more, but this is like the one that we had up there where it was 3 over 10 to the I. We break it down and we're going to have a to the 1, 2, 3, and so on until we get to infinity. If we add up these two, it's called the second partial sum because you're adding up just the two parts. And if you add 3 terms, it would be the third and so on, because you can't find what's called the infinite sum is going to be all of them. And that's going to be kind of like the thinking that we did. And you can only do that under certain circumstances where we got 3 tenths plus 3 hundredths plus 3 thousandths and so on. So we can say, hey, that's going to turn out to be this pattern of 0.3 repeating, which we know has this finite value. So a partial sum is going to be where you add up a certain number of them. The infinite sum is when you come up with a value that represents what they would all be added together. So we'll get some parameters around when that really works and when it doesn't in the next couple of days. But this is going to get you through 8.1b worksheet. So if you can knock that baby out and finish up 8.1a, then you'll be on pretty solid ground so that we can start talking about specific kinds of sequence and series like arithmetic and geometric, which would be so super duper fun. You're going to love it. Bye, guys.